All right, so today we're just going to dive right in because there's still a lot of review stuff to cover on acids and bases. You should have some vague shadow of a memory of the autoionization of water. So water reacts with itself as an acid and a base to form H3O plus and OH minus, and then it reacts back. And because water is always reacting with itself, there's always a tiny amount of acid and there's always a tiny amount of base in terms of H3O plus and OH minus in even perfectly pure water. It is a really, really tiny amount, but we can quantify that amount as Kw, which you learned in Chem 1, but didn't learn it as really an equilibrium thing, but it's an equilibrium constant describing the equilibrium amounts of H3O plus and OH minus in pure water. And so that's 1 times 10 to the negative 14, which we'll use a lot to convert between H3O plus and OH minus, because in water, if you add any acid, actually I think this is what this was, if you add extra acid, it'll react with water, forms extra H3O plus, but that also means that there's going to be less OH minus in the solution. And the more acid you add, the less OH minus there is. Or if you add a base, it will increase the amount of OH minus while decreasing the amount of H plus or hydronium. But those two concentrations always multiply to come back to 1 times 10 to the negative 14 because equilibrium, at least if the temperature is 25 degrees C. So tiny amounts. So the definition of an acidic solution or a basic solution depends on the relative amounts of H3O plus and OH minus. If I have more H3O plus than OH minus, then it's acidic. If I have more OH minus, hydroxide, it's basic. So if we wanted to determine the acidity of a solution, we have to calculate those or use what we know about a acid or base being added to determine how that's going to change the acidity of a solution. So which of these solutions is acidic? Which one's neutral? B is neutral. Yeah. B is neutral. Neutral solution. So this is neutral, which means anything that has more H3O plus than that is going to be acidic. And negative exponents can be a little bit deceptive because really, right, a larger negative exponent means an even smaller number. So this is 0.1234567. Well, up here, this is 0.123. This is 0.2345678 So which one's higher in concentration? A. I mean, this is part of the reason that we have pH. Because the concentrations can vary by so much. I mean, these are orders of magnitude different. So like I said, if there's a balance, or there is a balance between H3O plus and OH minus, if one increases, the other decreases by the same amount. And now in terms of equilibrium stuff, if we know, actually, let me write it this way, right? H2O, this is all from the autoionization of water, reacts with another H2O. One of them is the base, and I get H3O plus OH minus. These are both liquids. So if I want to calculate K for the autoionization of water, it's just the concentration of H3O plus times the concentration of OH minus. Bless you. And for water, K is 10 to the negative 14. So if I know OH minus, I can plug in 10 to the minus 14 equals H3O plus times, well, this is the OH minus concentration, so times 1.5 times 10 to the negative 2. And of course, I forgot my calculator. I'm so sad they got rid of slide over. It's a poor decision. So this is 10 raised to the negative 14 divided by 1.5 e negative 2. So this is 6 point, let's just do 6.7 times 10 to the negative 13 molar H3O plus. Is that more or less than 10 to the negative 7? Less. A lot less. A million times less. So is it acidic or basic? Or neutral? Basic. Basic. On this next one, 1 times 10 to the negative 7, is that acidic, basic, or neutral? Neutral. 1 times 10 to the negative 7, don't even need to do the math, that's neutral. Don't really need to do the math on this one either, but we will. H3O plus times 8.2 times 10 to the negative 10. I'm just going to edit this one. So H3O plus is 1.22 times 10 to the negative 5. So is that more or less than 10 to the negative 7? More. So is it acidic, basic, or neutral? More H3O plus? Acidic. More H3O plus, acidic. Cool. So lots of negative exponents. Negative exponents are confusing because bigger number, but bigger negative number is smaller. So, oh, and I guess the other thing with this is that, like, if we have to write all those negative exponents all of the time because we're talking about concentrations of H3O plus or OH minus, it's kind of annoying, which is why we have a pH scale. The pH scale is great. It's a simple, it's not even really a calculation. It's a transformation. We're taking data that is linear, and instead we're making logarithmic, meaning that for every 1 pH is not changing by 1, it's changing by 10 times. So a difference of 2 pH units is a difference of 100 times concentration. And really the P in pH means like log of, well, negative log of H. So if we want to calculate the pH of this solution, 5.3 times 10 to the negative 8, it is the negative log of 5.3 times 10 to the negative 8. That's not what I wanted to do. This is what I wanted to do. So negative log 5.3 e negative 8. 7.25 or 7.27. Really 7.28 because it rounds up. Now, if you have my favorite calculator, which I forgot in my office, it has one button for natural log and log base 10. So it's got one button, it says ln and it says log. You just press it twice. You press it once, it gives you ln. You press it again, it changes it to log. This is log, log base 10, instead of natural log, which is the natural base. So on the pH scale, instead of talking about all of these negative exponents and really having to pay attention to mostly those negative exponents, the pH scale essentially takes the negative exponent and makes it a decimal number. So 7, right, a pH of 7 is the same as 1 times 10 to the negative 7. So if the pH is lower than 7, or if the concentration of acid is higher than 1 times 10 to the negative 7, then it's acidic. And the pH scale is, or pOH, is just the log of the OH minus concentration. And it is possible to have negative pH values for really concentrated acids or superacids. That's the official name, superacids. Okay, so calculate the pH. Indicate whether it's acidic, basic, neutral. So negative log. Oh, that's not it. Negative log 9.5 e to negative 9. 8.02. Acidic, basic, or neutral? Basic. Higher than 7. Higher pH than 7 is basic. And I guess we'll use the way that we've done. Oh, okay, yeah, it's going to be later. That's fine. I'll just use the way that we've done, so that we've covered so far. So this is OH minus concentration. So if I want to calculate pH, I need to first convert it to H3O plus. And we can do that with the equilibrium constant of water. So 10 to the negative 14 divided by 7.1 e to the negative 3. That's real small. I believe I said 10. Nope, 12. And then I need the negative log of that. So acidic, basic, or neutral? That's the equilibrium constant for water. Kw. Acidic, basic, or neutral? Basic again. Even more basic. All right. Yes, going backwards. Actually, we've done some stuff with logs in this class already. So the inverse of a log, the negative log of H3O plus equals pH. Then I need to do log H3O plus, basically move that negative over to the other side, and then 10, wait. Oh yeah, because if I do 10 raised to the log and 10 raised to the negative pH, that undoes the log. So this is just H3O plus equals 10 to the negative pH. So 10 raised to the negative 8.37 oh, this is only 2 sig figs. Negative 9. Moving fast. Any questions though? Okay. POH is calculated exactly the same as pH. It's just the log, negative log of the OH concentration, OH minus. So the only difference is the number that we start with. We can also do this to our equilibrium constants. So pKa is the negative log of the Ka for an acid. Or we'll have later pKb. I guess you have pKw too. Negative log of the equilibrium concentration or constant of water, which is actually what is so useful here. So the relationship between pH and POH, we really just start with Kw and the concentration of H3O plus times the concentration of OH minus. And then we take the negative logs of everything. So the negative log of Kw equals the negative log of H3O plus times the negative log. Oh, well, this should be like this. Negative log of H3O plus times negative log of OH minus, which is the negative log of H3O plus the negative log of OH minus, because log rules. And then what is the negative log of H3O plus? Plus, nothing to sneeze at. It's pH. Negative log of H3O plus is pH. Plus the negative log of OH minus is POH. And then the negative log of Kw, Kw is 10 to the negative 14, is 14. So 14 equals pH plus POH. I usually like using this if I have to convert between like H3O plus and OH minus. I'll go to pH or POH first and then use this rather than doing the 10 to the negative 14 and dividing. It's easier to type into a calculator. But I present you with the circle of life, or the circle of pH actually. Because there's a lot of ways that we can convert between things. I don't know which one I usually put at the top. Let's do H3O plus. So if I have H3O plus and I wanted to calculate OH minus, I can go between those using Kw equals H3O plus. Actually, I have more room than this. I can use more room. Right, so I can convert between these using the equilibrium constant of water. I could also convert H3O plus into pH by taking the negative log of H3O plus, or 10 to the negative pH to go back. And I can do the same with OH minus, POH, or we can go back, it's 10 to the negative POH. And then we can convert between these two because 14 equals pH plus POH. So it's really up to you which way you want to convert. Just remember that when you're doing logs, rounding error is magnified in logs. I've never actually tried to like quantify how much it's magnified by, but if you round and then take the log of something, it's going to have a huge effect on what your number is. So keep some extra decimals. All right. pH of a solution gets, or increases, gets higher. What happens to the acidity of the solution? I feel like this is a trick question. Actually, I really just don't like the way this is worded. So as the pH increases, which means that if pH was, I don't know, let's say 5. If that increases, then it goes to 6 or 7 or 8. What happens to the acidity of the solution? Huh? You're saying increases or decreases? Decreases. Yeah. Decreases, becomes more basic. That's just some tricky wording. All right, perfect. Now we can get to the good stuff. So there are 2% potential sources of H3O plus in water, or a solution containing an acid. I should say a solution containing an acid. Because there's the ionization of the acid itself. So we've got one equation saying I've got acid reacts with water, produces H3O plus. But then water also autoionizes to produce some H3O plus. Not very much. It's like 10 to the negative 7. So down here it says, right, the autoionization of water can be ignored in all but extremely dilute acid solutions. So it says 10 to the negative 5 molar. That's because 10 to the negative 5 is 1, 2, 3, 4, 5. Autoionization of water will produce 10 to the negative 7. So 1, 2, 3, 4, 5, 6, 7. So that's 1% of your solution if you have a really dilute acid solution, 10 to the negative 5. So anything less than that, and then the amount of acid produced by the water will be more than 1% of all of the acid in the water. Not a concern with strong acids. So, right, by definition, strong acids ionize completely, meaning that if I add 0.1 molar HCl, the H3O plus concentration is 0.1 molar. And if I take the negative log of 0.1, I get a pH of 1. So does the autoionization of water matter when I've got HCl? No, not even a little bit. Now in weak acids, it might matter. And it depends on several things. For weak acids, we will have to do ice tables, but they're going to be simpler ice tables than most of the ones that we've done, at least for now. Because when I add an acid to water, remember, we'll have some acids that'll be like H3O plus, oops, not H3O plus, HPO4 phosphoric acid that's got multiple hydrogens. But this is reaching ahead a little bit. When we talk about something that's diprotic or triprotic, those hydrogens actually get removed one at a time. And so even with H3O plus, when this reacts with water, oops, even, what is it? Phosphoric acid, when this reacts with water, I'll get H3O plus H2 PO4 minus, which is very similar to this reaction down here, where I have some acid, that acid loses one proton, loses one hydrogen, the water gains that hydrogen, becomes H3O plus. So when we're doing this, this ice table is pretty much the ice table that we're going to have almost every time. And then at the end, we'll have to consider if H3O plus from water is significant at 10 to the minus 7. So I would recommend writing out the actual equation, the chemical reaction that's happening. So we've got hydrofluoric acid plus H2O, it's equilibrium, H3O plus F minus. And then we're giving an initial concentration, bless you, bless you again, of 0.25, 0 molar hydrofluoric acid Unless you're told otherwise, everything else is 0. And what about water? Just doesn't even matter for this. So I'm not even going to put a 0 in because I'm not going to like say negative x for water. It's all water. Again, like the liquids, solids, those kinds of things their concentrations don't change. So I'm just going to put a line through it. And then which way is this reaction going to shift? To products, because they're both 0. So my change here is negative x, this is x, this is x. I should say plus x. So 0.25 minus x, these again don't matter, x, x. And then we always want to be looking for a small x approximation if possible. Is a small x approximation, is it reasonable to assume that a small x approximation would work for this problem? Yeah, 10 to the minus 4 is my K. And we've got a decent sized concentration of hydrofluoric acid. So definitely worth trying. So I'm going to say basically the change in HF doesn't really matter. It's negligible. And then I get x squared over 0.25 equals 3.5 times 10 to the negative 4. Just like we did for all of our other problems. Honestly, easier to do it on here. So that's going to be 3.5 e negative 4 times 0.25, and then the square root. So x equals 0.009354. And then we want to check and make sure that our x is small approximation is valid. So divide that by 0.25. Times 100. And that's 3.7%. So that's good. Which means that my H3O plus concentration is just what I calculated for x. Because this is x, this will be x. And I mean, really, it's 2 sig figs because K is 2 sig figs. Now, do we need to worry about the autoionization of water? How much, I guess, what's the concentration of acid produced by the ionization of water? Autoionization. It's always the same. 10 to the negative 7. So this is 10 to the negative 7 is 0.1, 2, 3, 4, 5, 6, 7, which is insignificant compared to the amount of acid that we got from the hydrofluoric acid. So we don't need to consider this. We don't need to add it. Because it's like the same x is small approximation. You add it. Yeah.
When we add it to the H3O plus.
Right.
Oh, no, just
Yeah, maybe if you're calculating OH minus. All right, now we want to find the pH of an acetic acid solution. Acetic acid is one of those polyatomic ions you should know. But because we're given Ka, it actually doesn't matter all that much. It's HC2H3O2 plus water, H3O plus, C2H3O2 minus, and it's 0.015. Zero, zero, initial change, end, or equilibrium. So minus x, x, x. So what questions should you be asking yourself at this point?
Do a small X approximation.
Yep. Can we do a small x approximation? Can we? Probably.
Yeah.
Probably. 1 times 10 to the negative 5. It's real small. 0.015 is pretty small, but since our k is times 10 to the negative 2 times more or smaller than 10 to the negative 3, it should work. And so since we assume that that is negligible, then we can go in and this comes out to be exactly the same-ish as the last one. 1.8 e to the negative 5 times 0.015, square root of that. Oops, 1961 is 10 to the negative 4. Then we check our approximation. 3.5%, that's less than 5, so that works. So 5.196, wait, 2 sig figs. 5.2 times 10 to the negative 4. Ha. What are we looking for? pH, not H3O plus. So we need to do negative log. Now, do not do the negative log of 5.2 times 10 to the negative 4. Do the negative log of at least 5.19615. For every decimal you add, makes a smaller and smaller difference, but it would keep at least 2 or 3 past sig figs. Because that, if I do the negative log, will give me 3.28, which is the pH. What is the negative log of 5.2? Didn't actually end up mattering on this one. You get the same thing. Yeah.
It's just significant figures between like 4 and 2 decimals.
Logs. When you take the log of something, the first digit, or actually anything before the decimal, is not a significant digit. Right. Why? Because if I take this 3.28, I know here, I've got enough time that I can blitz through one more probably, but I can also show you this. So if I do, so why isn't that 3 significant? Because if I take the negative log of, or not the negative log, if I do 10 raised to the negative 0.28, that gives me 5.19. Actually, I should do more decimals. So 10 raised to the negative 0.28, 3, 9, 9, 6, 6, 5, 6, 4. Oh, actually, it's 1. No. Did I go the wrong way? Went the wrong way. That was right. That gives me 5.2, which 5.2 is, oh, that's because that's the, oh, right. I rounded, that's this. So the decimal portion contains this. And actually, oh, that's right. It's not even the negative. This should be positive. No, I was right. It's negative. So the 0.28 tells me that this part is 5.2, which is where all of my sig figs are, not the 10 to the negative 4.
So basically, if like the concentration has 2 significant figures, then the pH, like because of the log, is going to have in the decimals, it's going to have 2.
Yeah.
If it was 3 significant figures, then it would be 3 decimals.
Yeah. So in pH and POH, only the decimals are sig figs. The first number tells you the magnitude. I think this actually should be 10 raised to the 1 minus. Yeah, there it is. So like all of the really important information is all the decimal numbers. Everything before the decimal just tells me that that's 10 to the negative 4 or 10 to the whatever. It's the exponent part of the scientific notation. Logs are weird. Very useful, but weird. Oh, come back. Oh, and then again, we don't need to even consider, well, we need to consider the autoionization of water, because the autoionization of water is 10 to the negative 7. It's not going to affect this number with any sig figs. Yeah.
The log of the pH.
Oh, I took this one and I rounded it to get this. And then I took the negative log of this to get that. Really, I took the negative log of this, but they came out to be the same.
The pi is from the log, and then the exponent comes from the Ka that was given. Right?
This exponent? Oh, that was just from solving this. So I multiplied the 0.0150 times this, and then took the square root to get the x.
You're saying when we took the negative log, you want us to use the full, like all of the decimal places, like you have an x here, or
Use more decimal places. Yeah. Yeah. So like here, I think because this rounds to basically, like this rounds to almost exactly the same thing, then it didn't matter, and I got the same result. But if this had been like 5.15, so barely rounds up, then I would have probably ended up with a different number here. So it's one of those things that like sometimes it works out and it's fine. Other times you end up missing a question on a lab exam. There was a question on the lab exam that was like that. Which I think I'm almost done grading. Woohoo.
How bad did it look?
Not too bad. It's always hard to say. Like, it's not like I haven't graded, hold on.